Hello guys, my name is Dinesh and my project topic is vehicle routing problem using hyperheuristics. So the first thing is what exactly is a vehicle routing problem? The vehicle routing problem focuses on finding a set of paths a vehicle should take in order to deliver goods to the customer in an optimal way. And as we know that vehicle routing problem is an NP-hard problem and it is not able to solve those problem in brute force method under a given constraint of time. Because of that, so many heuristic approaches or other approximate based algorithms has been designed. And hyperheuristics is a such method which combines several low-level heuristics to solve this kind of NP-hard problems, and my project focuses on designing this hyper heuristic algorithm to solve for vehicle routing problem. So currently under my hyper heuristic algorithm I have used 10 low level heuristics, and these 10 level heuristics are under these four classes: mutation, crossover, local search, and ruin recreate. Mutation, crossover, and ruin recreate are also called as perturbation based heuristics, and local search is just a search based heuristics. And for the implementation of this project I have used an HyFlex framework. So HyFlex framework is an open source framework which is in Java, which provides a set of interface so which I can use in my project to create the problem objects and load the instances, and it also provide interfaces for all the low level heuristics. So in that way I don't have to focus much on the implementation of these low level heuristics and focus specifically on creation of this high level hyper heuristics algorithm. So uh, so for this project, I came up with my own hyperheuristics algorithm, which is based on genetic programming, and I also tried. I also used the binary tournament selection in genetic programming too. So my initial algorithm was like this: like initially, I created a k initial solutions, and out of the k initial solutions, every time I was selecting two random solutions, and on that two random solutions I was applying the crossover heuristics. So we can also consider these two random solutions as two parents. Applying a crossover heuristics on these two parents resulted in an offspring which may or may not be better than the parents, and on that parent, on that offspring, on randomly I applied then randomly I applied mutation based heuristics. So the offspring is being mutated, which in turn indicates that the solution might or might not be better than the previous solution. And again, on top of the offspring, randomly I apply the local search based heuristics or the ruin recreate heuristics to mutate the offspring, which might be a better one. So at the end of that, I was comparing the offspring with the two parents, and if the offspring is better than the worst of the two parents, then I was replacing the offspring with those. So in that case, in every iteration, I was able to replace the worst of the parents with the better one. In that way, the entire population was being improved, and these iterations has been run on a finite number of times, like 1, 10, 100,000, and 10,000, like that. And I was measuring the performance and the accuracy of the solution. More the number of times the solution more the number of times the iterations were run, better the solution was. But after certain amount of time, there was no improvement in the solution, and the solution accuracy was not good as compared to the brute force solution. And then I realized that uh, the reason the reason the solutions are not being improved is that there's something wrong with my initial algorithm. I won't say that it's wrong, but the initial algorithm is not smart enough to give the good better solution. So I tweaked the initial algorithm. So in the initial algorithm, I had only one heuristic patterns. Like I was applying the crossover, and on top of that, I was applying the mutation based heuristics. And on top of that, I was applying either the local search based heuristics or the recreate heuristics. And whatever the offspring comes, I was replacing the offspring with with the worst of the parents. And I was doing this for like n number of iterations. So to make this algorithm better, so I made some of the changes. One of the changes which I did was that instead of having one heuristic pattern of I had like m heuristic patterns for each iterations. So I was generating the heuristic patterns, and each heuristic under each heuristic patterns it runs a set of heuristics. like like in the report it shows one sample heuristic pattern which says like crossover heuristic of type 1, and after that I run the mutation based heuristic of type 1, and after that I ran the local search heuristic of type 1, and then local search heuristics of type 2 and type 3. In the initial algorithm, the entire settings were default. Like for the mutation based heuristics or the crossover heuristics or the recreate heuristic, the intensity of mutation was set to zero point 0.2, and for the local search based heuristics, the depth of search was set to zero point 0.5. Instead of that, I tried to create this randomness in this intensity of mutations too, because I realized that more is the randomness in the pattern strategy and more in the randomness in the intensity of mutation, and as well as the local search. More was the diversity being created among the population, and more the diversity is being created upon the population, better was the chance that the offspring which comes from this population has is might be better than the existing solution. So the algorithm was designed in such a way is designed in this follows. Like I have key initial population same, and I generate like m heuristic patterns, and I take each heuristic pattern and mutate itself. Mutating with itself means changing the intensity of mutation or the depth of search. So in that way, m heuristic patterns turn into 2m heuristic patterns, and after that I apply the binary tolerant selection where of these two m patterns I take two heuristic patterns, and I apply, then again I take two solutions from this k populations and apply apply the heuristic pattern on these two random solutions to give one offspring, and I compare the offspring which came from these two heuristic patterns, and whichever offspring is better, I will consider that heuristic pattern, and the other heuristic pattern I eliminate it. In this way, in each iteration I was keeping the better heuristic pattern, and I was discarding discarding the not so better heuristic patterns. So in that way, and so this way, all what I was doing that I was doing this thing until there was no more heuristic patterns were left, and all the better heuristic patterns were stored in a list. so which is as shown in the diagram in the template. So under each iteration I was doing this binary tournament selection. So after each iterations, the two things we could have observed, one is that the heuristic pattern strategy was being improved, and the other one is that the population was being improved. So in that way, and because of the mutation of the heuristic patterns, there was more diversity of the heuristic pattern strategy, which in turn results in the diversification of the population, which in turn results in the more optimal solution. So following this approach vastly improved my solution accuracy, and I was able to get the optimal solution in very less number of runs than as compared to the initial algorithm, which had only one heuristic pattern strategy, and the depth of mutation and as well as the depth of search were set to a default value. So making these changes has increased my accuracy by 41%. And on the other hand, it also clearly indicates that more the number of times the iterations has been run, better is the accuracy of the solution. And as well as if on increasing the population size, which in turn can be said as increasing the number of initial solutions also results in a bigger population or bigger population set, so which again in turn results in more diversification and under each iteration, which in turn results in the better solutions at the end. So at the end, the most optimal solution is just the most optimal solution from in all the intermediate solutions. So so the conclusion which from this project could be said is that heuristic hyperheuristic algorithm having a better heuristic pattern strategy and as well as randomness in the intensity of mutation and as well as in depth of set results in optimal solutions. And generation of hyperheuristic pattern strategy plays a very important role in the during this process. And on the other hand, one more feature which is very important uh, is using the binary tolerant selection algorithm, which ensure that after each iteration the heuristic pattern strategy is being improved. So the better of the heuristic patterns were being restored and the not so better were removed again. So these are some of the key points which I learned from this project. And on the other hand is that hyperheuristics are a very powerful research topic, and these same hyperheuristics can be used on other on other NP hard problems too. And one of the interesting things about hyperheuristic algorithm is that the same algorithm can also be able to work on different classes of problem without change in any part of the code base. So it's like I can run the hyperheuristic algorithm on bin setting problem or some other NP hard problem without concerning about the problem instance or the problem type and everything. So this is my project, and I would like to thanks Professor Rajnik for his guidance during this project and everything. And thank you.